Good morning student, myself Melissa Ankla, and in today's session structure analysis part 1 we continue with our topic strain energy, and in today's session we derive strain energy due to bending and torsion. Okay, first derivation is our strain energy due to bending, or we can say flexure. Okay, for that here I take a 3 figure. In this first figure, simply supported beam subjected to UDA load on entire span. Second figure, cut the strip. Okay, here I take a two transverse section, and third figure is cross section of beam. Now one by one I explain this figure and find out derive, or we can say derive derivation of strain energy due to bending. In first figure we consider two transverse section on beam and distance between two transverse section is dx. Clear? Section 11 and section 22. Okay, look at this 11 and 22, and this section distance is dx between them. And consider small strip. Here I take a one strip, and this area of this small strip is dA. Okay, and distance y from this neutral axis. Neutral axis is a axis where neither subjected to compression or tension. It is a constant layer of beam. Okay, and small strip, area of this small strip is dA, and distance y from this neutral axis, and bending moment in distance between this constant distance dx is also constant. Now in chapter of bending stress we derive one derivation, that is m by I is equal to sigma by y, and sigma we can write also f here. Okay, here I make a sigma as a subject, then m into y divided by I. Sigma is equal to stress, m is equal to bending moment, y is equal to our maximum distance from centroid, and I is equal to moment of inertia. Okay, our first sigma is equal to m by I into y. Clear? Okay, here I take one relation to prove this derivation. Now strain energy stored in a small strip, because we can't find out overall beam. First we find strain energy for small strip, then we find out overall beam. Okay, and area of this small strip is equal to dA. Now what is the equation of strain energy? U is equal to sigma square twice C into volume. Volume is equal to area into length. U is equal to sigma square divided by 2E into volume. Volume is equal to area into length. What is the area of strip? That is dA. And what is the length of this strip? That is dx. Okay, so here I write down dA and dx. Clear? Now U 1 by 2E, and value of this sigma that we already derive in starting of first derivation. Sigma is equal to m by I into y square. Okay, sigma is equal to moment divided by inertia into y square, dA into dx. Now one by one, strain energy U is equal to 1 by 2E m square y square divided by I square dA into dx. This is the strain energy stored in a small strip. Okay, first we find out strain energy stored in a strip. Now strain energy stored in an entire section of beam. Okay, again next step, this is for the entire section, and then we go for entire beam. Okay, for entire section we find out total strain energy, and this strain energy is between two zone, tension zone and compression, because here our beam is like simply supported. So simply supported beam is subjected to UDL load. Look at this. This is our simply supported beam, and this simply supported beam is deflected like this way, and this is our compression zone and this is our tensile zone. That means here I write YC because compression is top and tensile is in bottom zone. Okay, so sigma y is equal to yc according to this deflection. Okay, and y is equal to yt at bottom, and 1 by 2e m square y square divided by I square into dA into dx. Okay, clear? Okay, now next U total, that means here we find out our total strain energy 1 by 2e m square divided by I square and dx in sigma yc and yt y square into dA. Okay, common this term, separate out this term, and in bracket remaining term is y square into dA. What is y square into dA? Moment of inertia of area. Okay, moment of inertia of area, that means second moment of area. Second moment of area, that means our moment of inertia. So here I write down y square into dA is equal to I. Okay, dA into y, that means that is second moment of area, and second moment of area is nothing but that is our moment of inertia. 1 by 2e m square dx by I square into I. Okay, and this I and I cancel. U total is equal to m square, look at this m square 2ei into dx. This is the moment of inertia for entire section. Now we find out this is the strain energy for entire section. Now we find out strain energy for entire beam. This is our last step. And for find out strain energy for entire beam, I take a limit, and this limit is 0 to L. U is equal to limit of 0 to L m square 2ei into dx, and this is strain energy due to bending. Clear? First we find out strain energy for strip, second we find out strain energy for entire section, and third we find out strain energy for beam. Okay, and for that we take one transverse section. Okay, and this transverse section between two section 1 1 and 2 2, and distance between these two transverse section is dx. Then area of strip is equal to dA, distance from neutral axis is equal to y. Okay, and we use a relation of bending stress and derive our strain energy due to bending, that is U limit of 0 to L m square 2ei into dx. Next we derive strain energy due to torsion. Okay, this is our last derivation of strain energy. Okay, now our next derivation is strain energy due to torsion, and to derive this derivation, here I take a 3 figure. In this first figure, this is the plan of shaft, and this shaft is subjected to equal and opposite, that means this shaft is subjected to couple force F. And this first diagram is a shear stress diagram, and in this diagram at a center point our shear stress is 0, and from this center to edge outer surface shear stress is increased. From center is 0 and outer surface our shear stress is maximum, and this is the third figure. In this third figure our shear stress is uniform. To prove this derivation, we apply couple force on given shaft, and this force induce twisting turning moment in shaft, and we find out strain energy stored in a given shaft due to this torsion twisting moment. Okay, now we have already proved when our member subjected to uniform shear stress tau, then our value of this strain energy U is equal to tau square 2g into volume. This is the case of block subjected to shear loading, that means our axial loading. Now to prove this derivation, here I take a one ring. First of all we find out torsion of ring, and then we find out overall shaft. Okay, consider elementary ring, thickness of this ring is dr, and a radius from this center point is small r. Capital R is overall radius, and small r is equal to our radius of elementary ring. Clear? Okay, this is the first figure of plan of our shaft. This is second figure, varying shear stress distribution diagram, and finally this shear stress is uniform in our shaft. Okay, now strain energy due to torsion for uniform shear stress in ring. First of all we find out strain energy in ring. U R, that means strain energy in ring. R is the notation for ring. Tau r square divided by 2g into volume. V is equal to volume of ring and G is equal to our shear modulus. Here I take a ratio for tau r, shear stress in ring, and this is the ratio of small r to capital R into shear stress of overall shaft, okay, and volume divided by 2g. Now UR is equal to r square, then tau square, and this r square in denominator 2g into volume. Volume, that means our area into length, and this area is of elementary ring, and area of this elementary ring is equal to 2 pi r into di, and length L. Okay, put this value here. Volume r square tau square divided by capital R square into 2g, and volume 2 pi r into dr into L. Now one by one, r square into r, that means r cube, tau square, this two numerator and denominator cancel, pi L dr, and divide by this r square into g. Okay, this is strain energy for elementary ring. Now strain energy for whole section is obtained by integrating between range of 0 to d by 2, because at center point our r is equal to 0, and up to this r is equal to capital R is equal to d by 2, because at from center to this outer surface, and this r is equal to capital D by 2 for solid shaft. Now limit of 0 to d by 2 is equal to tau square r cube divided by r square g pi L, length of elementary ring, into dr. Okay, now one by one, constant term is separate out, tau square, then r square by g, then pi L, and integrate the term r cube. Okay, limit of 0 to d by 2, r cube into dr. Now integration of r cube with respect to dr is equal to r raised to 4 by 4, and limit is 0 to d by 2. Now what is r? R is equal to d by 2, capital D by 2. Okay, here our from this 0 to this r is equal to capital D by 2. Put this value capital D by 2. Look at this, tau square pi into L, a capital R square into your shear modulus, then r is equal to d by 2, that means d by 2 whole raised to 4 divided by 4. Here simplification, d raised to 4 and t raised to 2 raised to 4 is equal to 16 into 4. 16 4s are 64. Next, u tau square into pi L divided by capital R square into shear modulus, then d raised to 4 divided by 64. Okay, now tau square pi L, r, if I want to write down r in diameter, then d is equal to 2r and r is equal to d by 2. Replace of r, write down d by 2 and square, d square by 4 into shear modulus, then d raised to 4 divided by 64. Here d raised to 4 and d square, that means numerator left d square, tau square into pi into L, then t square, and this 4 64, 16 4s are 64, 16g. Okay, now take care here, tau square pi into L, then d square, and if I separate out this 16, 16 means 4 4s are 16, right here 4 4s are 16 into g. Now here tau square into L, and this pi by 4 d square is nothing but that is the area of our shaft, right here area. Okay, pi tau square into L into area, and in denominator left 4g, because here pi d square 4 I converted into area. Now finally tau square divided by 4g, and this area into length is nothing but that is our volume. This area into length is nothing but our volume. Okay, so write down volume here. Okay, again I am explaining you. U is equal to tau square pi L r square into g, d raised to 4 by 64. Clear? R is equal to capital D by 2, and square of this capital D by 2, that is d square by 4, because r square is right here. Now d raised to 4 and d square, that means in numerator left term is d square and denominator 4 16s are 16, 16 4s are 64, right here 16g, tau square pi L d square divided by 16g. Clear? Now for 16 is equal to 4 for the 16. 4 for the 16. Pi d square by 4 is equal to area. Tau square into L divided by 4g, and this area into length is volume. My final derivation of strain energy U due to torsion is equal to tau square divided by 4j into volume. Okay, here we prove strain energy due to bending and strain energy due to torsion. Strain energy due to bending is a limit of 0 to L m square 2ei into dx, and strain energy due to torsion is equal to tau square divided by 4g into volume. Okay, just now we stop here. In next session we start our example. Okay.